Welcome back, students, to one more session of your thermodynamics. We have already seen the different derivations. We've also seen the first law of thermodynamics. Then we also did one concept, that is internal energy. Now we'll come back to this concept that is called enthalpy, which is also called as heat content. So basically in thermodynamics, like if it is chemistry or even the physics, this one, so as the name suggests, heat content, when you speak about a system, how much ever is the heat or whatever changes are happening inside the system. See, basically in that thermodynamic system, you also know there's expansion, there's compression, isn't it? So these thermal changes, whatever are happening, and that too at constant pressure, is called enthalpy. So remember, if I have to write the definition, what do I write? Enthalpy is defined as, or it's taken as, the thermal changes. Thermal means heat, basically. Let us write that heat. So these heat changes, whatever are happening, what is the condition now? These changes should occur, or they will occur at constant pressure. That is important. At constant pressure. A bit cold, right? So at constant pressure is called enthalpy. Let us write that. So as I said, enthalpy is denoted by which alphabet? It is denoted by capital H, right? So this, if I have to write the formula for this, let us take the formula. It's denoted by delta H is equal to internal energy, which is denoted by U or E, plus P into V. Okay, this is delta H is equal to U and P plus P into V. So what is H? H is the enthalpy. What is U? U is nothing but the internal energy, right? P is the pressure, V is the volume. But what did we say? We said it should occur at constant pressure. Now I can write the same formula as, if I differentiate this becomes dH. Now U becomes du. Plus, there are two things. Once you are taking pressure as constant, you can write it as P dV, differentiate in terms of V, and here one more V dP, differentiate in terms of pressure. Now, if I have to speak about H, what is it? Whether it is state function or path function, it is a state function because it depends upon the initial and the final stages only, right? So let's write that H is a state function. So when I have to speak about, it's this one, like dH, whatever is there, this is the state function, and this dH is an exact differential which we have taken, isn't it? So this is the exact differential. Now what we are going to do, let us take two conditions now. So here I said this is the exact differential of H. Now let's take H1 is equal to U1 plus P1 and V1. This is one condition. Now I am going to take one more condition, that is H2 is equal to U2 plus P2 and V2. Fine. So I have two conditions here, H1, H2. I can write collectively as delta H, isn't it? So delta H is what? It's nothing but H2 minus H1. Right, so I will take together H2 minus H1. So write what is H2 equal to this one, this U2 plus P2 V2, right? Close the bracket, minus of U1 plus P1 V1. So now collectively I'll get all the U terms together, I'll get all the P terms together. So when I collectively get this, what do I get? I get this one, U2 minus U1. I'm getting this U1 this side, minus of, get this P terms here, P2 V2 minus P1 V1. Is it fine? Yes. Now you just, what is this now? H2 and H1. H2 and H1 is nothing but delta H, isn't it? The same thing. Now, so what can we write? We have U2 minus U1 here, P2 V2 minus P1 here. So collectively, what can I write? So at constant pressure, we said. Now at constant pressure, what will happen? Because we said enthalpy is a change at constant pressure. So this P2 will become equal to P1. Right? So P1 will become equal to P, because we have taken it as constant pressure. Now this whole quantity, we are left only with V2 and V1. Now let's write the formula taking this condition. What is that? It is nothing but delta H is equal to delta U plus constant pressure P, V2 minus V1. Isn't it? Yes. So how can I still further write this? I can write delta H is equal to delta U plus P delta V. Isn't it? This is one condition. Now when I have to take the same thing, this whole thing, what did we learn? P delta V. Since P delta V is nothing but work done, isn't it? So this is W. So let us substitute the value of W in this case. This becomes delta H is equal to delta U plus W. This is from Right. So what have we learned? We have already learned from first law, because first law we have a part of it in first law, isn't it? So from first law, what are we going to learn? Like what did we learn? We said delta U is equal to internal energy, change in internal energy is equal to Q minus W, isn't it? This is what we have. So instead of delta U, let us write this value. What do we get? Delta H is equal to Q minus W plus W. Yes. So minus W and plus W gets cancelled. So what are we left with? We are left with delta H is equal to Q. Now what is the pressure here? Pressure is constant. This is the most important thing. But what you should remember is, suppose if delta H value or the enthalpy value, if I get a positive answer, suppose if I get delta H value, if I get a negative answer, whenever you get a positive value of delta H, that means the process is endothermic in nature. Remember this. Suppose if you get delta H value as negative, then I can say the process is exothermic, right? So hope you have understood. I started with saying that it is a heat content. What is the condition? At constant pressure. So I have taken two things. What did I say? I have taken first H1, delta H is H1, and this to H2, because it is exact differential of H. Then I have taken the common terms on one side. Then I have written this. Then I related to the first law of thermodynamics, and finally I got this. So delta H is equal to Q, the quantity of heat or the heat content at constant pressure. I came to that concept only, isn't it? Yes, fine. So now let us write one more important thing. Now we'll see the relation between delta H and delta U. Let us write the heading: relation between delta H and delta U. So when I have to take the relation between this, what did we write according to first law? Because basically you have this in the first law, isn't it? So let us write the first law first. According to first law of thermodynamics, what do we get? We have got delta U is equal to Q minus W, isn't it? Yes. Now what is W? It is nothing but P delta V. We have already written, since W is equal to P delta V, substitute that value here. Now what do I get? Q is equal to Q minus P delta V. Yes. Now at constant volume, suppose if I take constant, because I have to relate between H and U. So what will happen when I take constant volume? Constant volume means delta V is change in volume is 0. Then what will happen? This whole quantity will become 0, isn't it? This is the condition. Then delta U is equal to, or this whole, like if I make this as 0, what will happen? Delta U will become Q. But what is this? At constant volume. This is the condition. Earlier it was constant pressure. Now this is constant volume. This clearly shows. Now what do we know? In the earlier thing we have studied delta H is equal to QP. This also we have studied in the enthalpy equation. Delta U is equal to QV, delta H is equal to QP. Now we will just see how can I relate both. So when I have to take that equation for delta H, let's see. So what do we know from enthalpy? Enthalpy is the heat content is U plus P delta V. This is what we have written. This is what we have learned from enthalpy derivation. Right. So now let us assume there are n moles of gaseous reactant in this. Let us assume that. So here I'll just take there are n1 moles of gaseous reactant. So right. So then what happens when I am applying or this gaseous reactant? I'm maintaining conditions of constant temperature and pressure. Fine. So what happens when you maintain that the temperature, that constant temperature and pressure, N1 is going to get converted to N2. That reactant changes to N2. Then what will happen? According to the ideal gas equation, PV1 is equal to N1 RT. Basically PV is equal to nRT. Now from N1 mole it is converting into N2 moles. PV2 is equal to N2 RT. Isn't it? Now let us get the things together. What will happen? PV2 minus PV1 is equal to N2 RT, because I've got the common terms together. N2 RT minus N1 RT. Isn't it? Now, so what can I further write? Because V2 minus V1 is delta V, isn't it? So let us P delta V is equal to, this can be the N2 minus N1 can be written as N delta gaseous reactant, RT is common. Now what is Ng? Ng is nothing but 1 mole of the gaseous product minus moles of the gaseous reactant. Remember that once again. Ng is nothing but mole of the gaseous product minus mole of the gaseous reactant. Yes, so remember. Now what can I write now? Like, let us go back to the reaction and see. I can further write, as because P delta V is equal to this one, I can go back to this equation where I have written delta H value. So therefore I can write delta H is equal to delta E plus delta Ng, because instead of P delta V I can write this value, Ng RT. So this is your relation. So whenever they ask you the relationship between delta H and delta U or delta E, both are same, isn't it? So this is the final relation between delta H and delta U. Thank you for watching, students.